Okay, so there are a couple of potential announcements for the course. I want to put those on the Moodle instead of embedding them in the YouTube videos. So here is a hint to look at the Moodle. By the time you see this, or shortly after, I should have some weekly course announcements up. And here is also a reminder to sign into the course den before you sign into the Moodle as well, because they will be checking course den usage. So skipping over our announcements, this week we are going to start talking about neural networks. So last week we discussed gradient descent in the abstract, and I used gradient descent to train a model for a line. This week we're going to talk about actual neural networks as such. We're going to talk about how we train them with gradient descent, and then we're going to build a Numpy version. Okay? So neural networks are a universal function approximator. And by universal, we in fact mean Turing equivalent. So, if we have a paper that provides us with a model that allows us to map every Turing machine to a neural network and convert, it allows us to map every Turing machine to a neural network. We know that for every neural network there is a Turing machine because we train neural networks on Turing machines, right? So, if we know that the set of all neural networks is less than or equal to the set of Turing machines, and that the set of all Turing machines is less than or equal to the set of all neural networks, we know that they are equivalent sets, right? So these kind of results maybe tell us that in principle a neural network is a universal function approximator, but they don't necessarily tell us what the computational power of a specific network is going to be. The production that produces a neural network for a Turing machine assumes the neural network has infinite input layers and assumes it has infinite precision. Obviously, real networks don't have that, or don't meet that property, right? Real networks obviously have finite units, they obviously have finite precision. We do not necessarily have as good a handle on what the computing power of a specific exact network is relative to a certain problem. There is a literature on that, there are statements we can make about that. I am not familiar with that literature. I may already have stepped out of my depth a little bit, so I'm just going to go ahead and stop being stupid. But we do not, but yeah, neural networks are in principle Turing equivalent. We do have a good training scheme for them. Note, good is not perfect. Again, there are situations where we know that if a problem is soluble, there exists a neural network that can solve it, but we also know that we cannot train neural network architectures to converge to that solution, right? So in the specific case of the recurrent neural network, for example, we know that there are problems, that recurrent neural networks can solve because we know that they are universal, right? They can solve any problem. So we know there are problems that neural networks can solve that we also know they will never converge to a solution of under gradient descent, right? So we have a good training scheme. We do not have a perfect or universal training scheme, right? So they're Turing equivalent, although we maybe don't necessarily know how to map a specific neural network to a specific problem. And we have a good training scheme for them, although it is not necessarily a perfect training scheme. The weights are the parameters that we tune, right? So we were talking about sort of a set of parameters theta that we tune, and for neural networks, that is the weights, and we will see later biases. There are also hyperparameters, but we're not going to worry about that right now. We'll talk about hyperparameter tuning later. So hyperparameters are sort of the architectural details of your network, and maybe some other details that you make during training and design, like the learning rate, that sort of are treated as fixed or constant while you are tuning your parameters, right? So hyperparameters sort of determine the capability and behavior of your network, but we don't usually think of them as being part of theta, right? The parameters that we're tuning with gradient descent is just the weights and the biases. So here is a schematic of your basic neural network. The input/visible nodes are these pink ones here. The output or hidden nodes are green. And the connections between them are indicated with these arrows. Note that this is fully connected. There exists between every input node and every output node a connection, right? Notice also that there are no recurrent connections, right? So you don't see you don't see input to input connections, you don't see output to output connections, and you don't see like loops, right? You see the total connection from every input to every output, and that's it. So notice also that each output has a nonlinearity, represented by this sort of squiggle. We'll talk about that in a little bit. All right, there might also be biases. Oh, damn it. But we're not going to worry about that right now. And a sort of historical note, why does it keep shifting off? Stop it, there. As a sort of historical note, you will sometimes see people refer to this sort of basic structure of a network as a perceptron, right? People often need a word that means a basic bargain bin vanilla network that is not an RNN or LSTM or RBM or whatever else, and they often just kind of settle on perceptron. This is debatably. Anyway, they often settle on perceptron, right? That is technically incorrect. Technically, the perceptron is a specific historical network that has a specific weird activation function, right? It is a thresholded network. This is not technically a perceptron. I am going to avoid describing this thing as a perceptron. I am going to refer to these as ANNs or feed-forward networks. Okay. All right. So, there we go. All right. So the forward pass. So in the forward pass, we're going to compute the output of our system, and in the backward pass, we're going to adjust the weights. The forward pass consists of... Intuitively, what we're going to try to have happen is we're going to set a value to these input units, which I will index with I, and then we're going to compute the total input from each input unit to each output unit, which I will index with J. And again, that might not be the most obvious index. That is because that's what the paper that I'm trying to mostly follow uses, right? So input is I, output is J. And we're going to adjust them, right, weight them by these connection weights, okay? So we're going to multiply each input unit's value by the connection weight and then sum them to get the pre-input or pre-activation to a given output unit, J. Okay? So multiply the input unit's state by the connection weight and then sum all of that to get the pre-input. And then, to get the actual output or activation, we're going to apply the specified nonlinearity. Okay? So, that looks like this, right? Sum over, whoopsie, there's my writing pen. So the state of hidden or output unit, right, J, indexed by J, is the sum over all of the visible units indexed by I of the connection weight between I and J times the value of I. Right? So sum over this. Then, so all of this right here is the pre-activation. Then we're going to apply this, which is the nonlinearity, or activation function, to get the activation or output. Okay? So sum over input times weight gets us the pre-activation. Applying the activation function or nonlinearity gets us the activation, i.e. output. Okay? And it turns out that having this nonlinearity here is actually important, because if we didn't, for technical reasons, no matter how many layers we had, we could never exceed the power of one layer. It's a sort of linear algebra property, right? In order to actually learn sort of any function and exceed the computing power of one layer, we have to apply these nonlinearities in sequence. Oops, there we go. So if we do that in Python, that's going to look like this, okay? So here I'm declaring like a list of numbers to be my visible layer state, declaring a two-dimensional-ish kind of list of weights to hold my weights, and I'm declaring a list to hold my output. Then, for each j in the number of hidden units I have, that's 2, because I am trying to mimic this network, right? So 2 input, 3 output. For each j in the number of hidden units I have, I'm going to set up a thing to kind of build the pre-activation in. I'm going to compute that product of then I'm going to loop over I, indexing each visible unit. So 3 is the number of visible units. I'm going to get the value of the ith visible unit, multiply it by the connection between I and j, and then add that to that accumulator variable. Then I'm going to append that to that list. So at this point, H has the pre-activations in it. Of which there are 2. Then, to get the actual activations, I'm going to use this list comprehension to build a new list that is the result of applying the tanh function, the hyperbolic tangent function, to every hj I cached, right? For hj in h, right? And that is going to get me the forward pass output of this network. So if we actually run this in Spider, we're going to see that that is 1. The reason is, at this point, right, these are large-ish numbers, where our definition of small would be between 0 and 1, right? These are going to be much greater than 1, because you're looking at the sum of 1.0 times 11 plus 2.0 times 12 plus 3.0 times 13. Okay? Now, the tanh function, whoopsie, I closed this window, asymptotically approaches 1 and -1, right? It looks and I'm fiddling with the graph.tk window, but you can't see it. It looks like this, okay? So, we are asymptotically approaching 1 at positive infinity and -1 at negative infinity. But note also that we're pretty close to 1 at 2, okay? So if we are approaching 1 at infinity, but we're pretty close to 1 at 2, then what do you think tanh of 70-something is going to be? It's going to be pretty damn near 1, right? It's going to be closer to 1 than this is. So our pre-activations are going to be large, and our activations will be 1. If we actually run that in Spider, so I've copied over my code into Spider. I clicked the green arrow to run it. Nothing printed because I don't have any print statements, but if I examine what is in H, I get 1. And if I want to modify this so that we don't apply the activation function, I can comment out this line that applies the activation function. I can save it. I can run it. Oh, and you can't see the mouse pointer, so you just see magic stuff is happening. I apologize. But if I run it, now we see what my pre-activation was, 74 and 134. And if I apply that, if I apply the activation myself in H, there we go, right? So basically we see that it's saturating. Because the input is huge, the output is arbitrarily close to 1, right? It is within floating point precision, effectively, of 1. That means that we're losing a lot of information here, right? So the sort of information gain of inputs of 74 and inputs of 134 are basically the same, right? We have saturated our unit. Oops, damn it. I really wanted to stop doing that. So, this annoying sum, right, this multiply and sum, ends up being mathematically the same as multiplying a matrix W by a vector V. Okay? So now let's take a moment to talk about matrices. Stop it. So we can write the forward pass simpler with matrix notation. Matrices represent linear systems, but linear algebra is kind of a deep topic. Fortunately, right now we don't actually care. The only thing we really care about right now is matrix multiplication, right? So here I've written a couple of matrices mathematician style, and I'm computing a matrix product. So instead of thinking about linear systems, though, here's another way to think about it. Matrix is how mathematicians pronounce 2D array. It is basically just a regular rectangular box of numbers, right, in which each number has an index. So it is very much how a mathematician might describe a 2D array. Besides just being a 2D array, it has a couple of useful operations defined for them, like multiplication, right? And here, I am using, incorrectly, the @ symbol to mean matrix multiplication, right? So to multiply two matrices, you basically just go across the row of the left one and down the column of the right one. Oops, stop that. I don't know why it keeps going to desktop. Ampersand, or sorry, @ is not the usual notation for this. There's a specific reason I'm doing that. That's because that's the notation that Numpy uses. So, this is the formula to compute a cell in the resulting matrix given the left and right matrices, right? The cells in the left and right matrices. Notice that it's pretty close to the thing that we were doing before to get our pre-activation, right? If we cross out this I and this I, right, then we basically have the formula for hidden unit J, right? And notice that this one is square, right? Basically, these are 2D. If we assume that this one was width 1, right, and that this index could be omitted, then we'd basically have the math to give us our output, right? Tripping a little bit. So just to be clear on what's happening, we can sort of expand that like this, right? So what you're going to do is you go to get the to get a specific cell of the output, in this case the 1, 1 cell. We're going to go across the first row of the left matrix and down the first column of the right matrix, multiplying as we go and then we're going to sum it, right? So A1, B1, which is this and this, plus A12, B21, which is that and that, plus A13, B31, which is that and that. And we're going to sum all of that, right? And that's the math we were doing before. So notice that the dimensions have to line up, right? The width of the left matrix has to be the height of the right matrix. Notice also that their dimensions determine the output. The height of the left matrix and the width of the right matrix determine the height and width of the output, right? So the height of the left matrix determines the height of the output, and the width of the right matrix determines the width of the output. I may have transposed that. And that's sort of summarized right here, right? So an M, where M is the width, times an N, where N is the height, matrix, times an N, these have to be the same, where N is the height, times O, where N is the width, produces an M by O matrix. Okay, so I didn't transpose. That's right. Note also that this is not commutative. That's a fun word. Commutative. Commutative. All right. Which just means that A times B does not have to equal B times A. And in fact, B times A might not even be possible. The dimensions might not line up. Right? So for example, if we had a 3 by 2 matrix times a 2 by 4 matrix, it'll work this way, and you will get a 3 by 4 matrix, but it won't work the other way, right? Because then you would be trying to do a 2 by 4 matrix times a 3 by 2 matrix, and the dimensions don't match. Even when they do match, the product will not, or doesn't necessarily have to be the same. All right. So sometimes I'm also going to talk about row and column vectors. A row vector is a matrix that is height 1, right? So it's height 1. It's one row. A column vector is a matrix that is width 1. It's one column. So if a matrix is how a mathematician says 2D array, then it sort of looks like this might be how a mathematician says 1D array, right? Or just array. So why do I care about whether it is 1 by 2 or 2 by 1? Well, the reason is when we are performing matrix vector multiplication, these produce different things, right? Remember that these dimensions have to line up, right? One way it will work, one way it will not. If I have a 4 by 4 matrix, then multiplication by a 4 by 1 column vector makes sense, right? That is a 4 by 4 box of numbers times a 4 by 1, yeah, that's 4, column of numbers, which is going to produce for me another 4 by 1 column of numbers, right? But 4 by 4 times 1 by 4 doesn't work, right? I can't multiply a row matrix there. That's not going to work. That isn't defined. So it's going to be a little bit of an irritation for us, but not a big one, that if we want to use a linear algebra library, which we're going to do, we're going to have to make sure that our matrices stay the right shape, which for us, for now, is going to be column vector. All right. And I guess this slide just kind of repeats that, right? So m by n times n by o is m by o. Notice two special cases of that. If I have a row vector times a column vector, I just get one number, right? We go across the row, of which there is 1, and down the column, of which there is 1, multiplying, right? We sum it up, and we just get a number, right? So this just combines a row vector times a column vector is just one number. Conversely, a column vector times a row vector gets us a matrix, right? Because there it is an m by 1 times a 1 by n producing an m by n. Okay? So if row by column sort of collapses, column by row explodes into a whole sort of box of numbers, where each one of these things is just the product of one row. So again, we go across the row, of which there are many, but their width 1, and then we go down the column, of which there are many, but their height 1, to get each one of these cells. So C11 is A11 times B11. C22 is A21, times B21, or B12. Okay? And I'm going to say at this point, if this notation is sort of overwhelming you a little bit, right now I think you can basically just sort of think of what we have is a box of numbers that we are putting our weights in. Right? That is analogous to a 2D array. And that we have some notion of multiplication times our input vector that is useful to us, right? So that's the thing that you should focus on. We have a 2D array / box of numbers of weights and a notation for applying that to our input vector. Okay? All right. So in a couple of little bits of notation we'll need. Sometimes we apply a function component-wise, that is to every element in the matrix, and what that means is just this. Okay? So if A is a
Screen reader on.
Stop
22 push button. Screen reader off.
There's a miss feature. All right. So if A is a matrix, and I write tan H of A, what I mean is tan H of the matrix, and what I mean is the matrix of the result of applying tan H to all the stuff in the matrix, right? So tan H of A1, tan H of A2. And it's worth sort of understanding what that means, because there are a couple of times where we're going to need to understand that we're applying a certain operation component-wise. When I say component-wise, what I mean is going through the matrix component by component and applying it to each element in there. Okay? So armed with all of this, the end result is we can write our forward pass very, very concisely, right? It's just this. And I'm gesturing at the screen, but you can't see it because we're just recording my screen. H is a j by 1 column vector of our outputs. W is a j by I matrix that has our weights in it. V is a 1 by is an I by 1 column vector that has our inputs in it. And then tan H is our nonlinearity, which we are applying component-wise. Okay? There's actually a lot that is happening here. It is just very, very concisely expressed. All right? And again, if you're feeling a little overwhelmed, just focus on this W is the thing with our weights in it. We're applying those weights to our input, and then we're applying the nonlinearity to the result of this, right, to the preactivation. Which again, the preactivation I will sometimes write as Y. Okay. Oops. And here's sort of an illustration of what this kind of looks like. So if we're going to think about this as boxes of numbers, we've got something like this, right? Where here is sort of a representation of the 2D array / matrix that has our weights in it. Here is the column vector that has our inputs in it. And then here is the column vector that has our outputs in it. Okay? So this is a graphical representation of at least that, right? I have omitted the tan H from this schematic. Yep, column vectors. A short note, I actually don't think the term column vector is universal. I picked that up from a physics professor in undergrad. I use it because it's useful for talking about an important property here, right? Because the dimensions have to line up, there is a difference in a 1x3 column vector, 3x1 column vector and a 1x3 row vector. I have had people from other disciplines stare at me like an idiot when I say column vector or row vector, so I think some other schools of math in physics and science that deal with matrices and vector multiplications maybe don't use these terms. All right. Okay. We'll also need the transpose. The transpose is really, really simple. We're just flipping the matrix, right? So we're taking a matrix, and the I by j term of the transpose matrix is the j by I term of the original matrix, which is to say we're flipping it. See? Here's our original matrix transposed to this. We flipped it. Oops. This one. All right. So, can we work with matrices in Python? We can, with Numpy. Numpy gives us efficient n-dimensional arrays, i.e. matrices, a bunch of convenient matrix operations, like transposition and multiplication, a bunch of linear algebra functions that we don't need right now, and a bunch more stuff that we also don't need right now, right? But it gives us efficient multidimensional arrays and a bunch of useful matrix operations. Those are the important ones. So Numpy matrices are backed by C arrays, and many of Numpy's operations and functions are written in C, which means they're going to be much faster than interpreted Python code, right? Remember, I said earlier that Python code is up to a factor of 100 times slower than the analogous C code. Well, that's not going to be true of NumPy functions because NumPy uses C to implement most of the operations on matrices. That means that just by using NumPy... Why are you not advancing? Advance. There we go. That means that if we can write our neural network code using NumPy matrices, it'll be easier to write because that matrix notation is so concise, right? Our whole forward pass is written like this, right? That's pretty damn concise. Remember how annoying that double sum looked? There's a reason I didn't go through it in great detail, and that's because it can just be written like that with NumPy matrices. And, besides being much more concise, it'll be about 100 times faster than if we wrote it using Python, because the matrix vector multiplication will happen in C. And the tan H function will also happen in C. Most NumPy things happen in C. So, simpler and faster? Win-win. Go us. All right. Also handy is that NumPy arrays are kind of a lingua franca for a lot of Python scientific packages. If you're going to try to go Latin, don't screw it up. Or is lingua franca French? I don't know. Good job, me. But yeah, many other Python scientific libraries use NumPy. So if we learn some NumPy, that's going to be a repeatably usable skill. So, stop that. I don't know why it's doing that. So here is our forward pass in NumPy. And you kind of see, so yeah, it is very concise. You kind of see, excuse me. Sorry, all right, you kind of see why I wrote this the way that I did before, right? In fact, you might recognize this as the way that I wrote our our 2D array of weights before, right? So I'm just doing numpy.array and giving it this list of lists as an argument. And why did I make it a list? So a list of lists of numbers? Because I wanted to convince it to be a column vector. This is why we talked about this before. This is part of why. NumPy array of 1, 2, 3 is not even a matrix. This is important. This is not a matrix. This is just a 1D array. And if you try to multiply this by a matrix, it will, I think, work. It just will not do what you want it to do. Okay? This is one-dimensional. It's 1D. This, right, a list of lists, would be 2D, so it would count as a matrix, but it's a row vector, right? It is a 1 by 3. So at least this is a matrix, but it's not the shape of matrix we want. You gotta do this to get a 3 by 1 column vector that is the shape that we want. Okay? But with my 3 by 1 column vector that is the shape that I want, and my 2 by 3 weight matrix, I can just multiply that weight matrix by that column vector, apply the hyperbolic tangent function component-wise, and shabam, there's my output, right? This is much more concise than having to write that double sum by hand. For very large matrices, it is also going to be much, much faster. Hopefully by now, so this is the point, if you can get as far as this is the forward pass, this is a box of numbers that has our weights in it, this is a column of numbers that has our inputs in it, and then this is a matrix multiplication that applies weights to inputs, you're good. That's what you really need to have right now, okay? If you haven't quite untangled some of that sum notation stuff, it might be useful. You don't have to worry about that right now, right? Right now, we just need the intuition, box of numbers with weights, column of numbers with inputs, application of box to columns, all right? Oh, right. This is also the second dumbest weight initialization possible. I can think of a dumber one. This is the second dumbest weight initialization possible. So, armed with our forward pass, we now need a backward pass, right? So what we need to do is define a loss and define a loss, compute the loss after the forward pass, and then adjust the weights to reduce the loss. Problem, how do we figure out what our weight update is? The daemon calculus. Praise calculus. Futurama might be before y'all's time, mightn't it? I might have just revealed how old I am. Maybe the kids don't watch Futurama anymore. Yeah, that was, didn't that start in like 2002 or 3 or something? Yeah, that might be. Now I feel old. Well done, me. Well done. Anyway. Nah, I choose to believe Matt Groening is timeless. So again, this font is wrong. This should be a curly L. So we need a loss function to measure our error, right? It needs to map Rn to R. It should be Rn times Rn, but good job, me. Be differentiable and make sense, right? We talked about these before. So it turns out that mean squared error is a common choice, right? Mean squared error works fairly well for this. So mean squared error looks like this. And the name is accurate. So if we kind of, maybe it looks like a box of math symbology, but let's take it slowly. It is the difference in the desired behavior in the model, which is the error, right? That's just the error, squared, averaged, right? Sum over all p of them and then divide by p. It is the average of the square of the error. Why square the error? Because it takes care of sign. If this number is negative, right, squaring it produces a positive. If this number is positive, squaring it produces a positive. This is kind of a way that we can only care about the magnitude and not the sign of our error. Oop. Stop it. Oh my God. Okay. I'm really... I tell you every slide transition. I don't know why it does that, and I'm sorry. I need to stop doing that. So this also has the property that it produces one number, right? So it maps two real vectors. Good job, me. Two real vectors to one real number. That was one of the properties. It's differentiable, so I'm not going to go through this and differentiate this, but if you try to reach back to your calculus, everything in here should be a thing that you know how to differentiate, right? You know how to differentiate summing, you know how to differentiate subtraction, you know how to differentiate squaring, you know how to differentiate multiplication by a constant. So it's differentiable. And it makes sense, right? As the difference between d and m grow, this error term will grow. Its square will grow even faster, right? And then if we average them, we'll average together like a bunch of terms that might be large and might not, right? But we'll be combining the error signal from all of our different terms, right? So as d and m diverge, this number is going to get larger, and when d and m are very close, this number will be close to 0. Blech. This 1/2, so yeah, that 1/2 term is not there in the version that you look up on Wikipedia. That is going to be so we can make the math work out nice when we start differentiating this thing. That is to make the math work out nice when we start taking derivatives of this thing. All right. So what we actually want to know is how a change in weight is going to affect the loss. Remember? We talked about this last time, right? So since the loss isn't directly a function of the weights, we're going to need to use the good old multivariable chain rule, which looks like this. If you haven't had multivariable calculus, these are partial derivatives. You can replace them in your mind with the normal derivative from calculus, and you'll be close enough for our purposes right now, right? So what we actually want is the derivative of this outer function, which might be the loss, by some term that might be the weight. We're going to use the good old multivariable chain rule to get it. I'm not going to make you do that. Here, I hate you, Libra. I hate you, OBS Studio. I hate whatever is doing that. All right. Here is the thing that we're going to wind up with. The derivative of the loss with respect to a specific weight is the error times the derivative of our activation function right, which would be tan h evaluated at the pre-input, right? So derivative of the activation function at the pre-input times the corresponding input term, right? So remember that each weight maps an input to an output. It is the, oh, I think I flipped those. It is the output term, right, for the error, the error and the derivative of the activation function and the input term, right, for x, which is that in matrix. No, go to hell, screen reader. Is this in matrix notation? And it really is going to be about this concise when we write it in Numpy, right? So if your head is kind of swimming at what this math would actually look like if you tried to write this as like a double sum of who knows what, don't worry about it. It is this in matrix notation, right? Where this and this are column vectors. This is also a column vector. This is a column vector that we're transposing. And when we multiply, so it's a column vector that we're transposing, so it's a row vector. And when we multiply column times row, we get a box of numbers that is the size of our weight matrix. Real convenient. Okay? All right. And, stop it, damn it. That really is what that's going to look like in Numpy. This is component-wise multiplication. So again, that's a column vector, that's a column vector. Subtracting them component-wise is a column vector. And then we're going to multiply it by the derivative of our activation function. This is just a function I'm going to write to produce the derivative, right? And we're going to multiply it by our input flipped so it's a row vector, and that's going to blow up into the updates for our weight matrix, right? So it really is that simple in Numpy. And again, not only is it, so some of you might be thinking, simple? What? This is simple compared to if we had to write out that block of God only knows what sums, right? That would get real fun after a while. This is much, much simpler. If you get an intuition for what matrix vector multiplication is, it's fairly understandable, and it's fast. That's the other really important thing, is that this is going to be very, very fast compared to the pure Python code, because Numpy will fall back on C functions to do that. Yep, we know that. So we want to take a small step down the gradient of the loss. Why? Stop. All right. So our net remains stable, okay? And so it still remembers early inputs. We talked about this very, very briefly. Basically, we want to take little bitty steps, right? And I drew in class on Tuesday for some of us a function of us trying to kind of walk down a valley, and if we have small steps, we walk down the valley incrementally, but if we take big steps in parameter space, we might actually leap all the way across it, right? Oops. And if we keep taking big steps, we might actually climb out of it. And we want to find the minima of this valley, right? So small steps are good here. That's what we mean by stability, basically. Another way to kind of think about that is if the learning rate is too large, then the network will be placing very heavy emphasis on whatever it just saw, possibly to the point of sort of ablating information from earlier inputs, right? So it might be getting better at the stuff we just showed it at the expense of getting worse at the stuff it saw a while ago, right? Which is bad. Erase, disable, good. So to achieve that, we are going to multiply our updates by a small number that is the learning rate, or LR. I can't think of the phrase that I'm looking for here. Different weight update schemes, and we're going to look at more of them, are going to use different ranges of learning rate. For good old stochastic gradient descent, something between 0.1 and 0.01 is going to be a good starting guess. So, yeah, stochastic gradient descent is the scheme that we're going to be using. Stochastic gradient descent is both surprisingly simple and surprisingly effective, while not some stopping condition. So while it isn't time to stop, there we go. We're going to pick a sample at random, compute the activation of the sample, compute the update, and then apply the learning rate times that update, right? So it's really straightforward. It is called stochastic, right? Stochastic being a sort of $20 word for random because of this step right here. Select a sample at random, okay? This is as opposed to batch learning, where you would compute your loss across the entire data set before performing a weight update. It turns out that stochastic gradient descent might be a little bit noisier, but it's dramatically faster, right? Computing an update and then applying it for every single sample might seem like it would drive the network crazy, but it actually produces better networks. It's much, much faster, and the results tend to be slightly better. So again, compared to sort of old school full batch learning, this is a dramatic improvement. There is also mini batch learning, which is where you're going to compute the update across some subset of the original input. Let's say that you have 1,000 inputs. You might do them in batches of 20, right? Where you compute your loss and weight update for a mini batch of 20. We'll talk about times that you're going to do this later. There are some techniques that only make sense, that are only really defined in a mini batch environment, right? But to start with, we're going to work with SGD, stochastic gradient descent. Really straightforward, really effective. So putting all of this together, armed with our sort of magic formula for brain fade, armed with our sort of magic formula for the weight update, armed with our matrix vector notation, and armed with stochastic gradient descent, we can finally write a single layer single layer neural network with NumPy in Python, right? So I'm importing NumPy as NP. This as NP you may or may not have seen before. This is a way to rename this package. It is almost universal to the point that any tutorial you find is likely to refer to NumPy as just NP. So I'm going to create, oh good lord. All right, this is an art class, screw it. There we go. I'm going to create my random weight matrix, okay? This is the low value, this is the high value, this is the shape. So you might say, wait a minute, didn't you just tell us that this is going to be a row vector? It is. It's a 1x2 matrix because when I'm going to train it to learn, did I write that somewhere? Oh, okay. This thing is designed to learn functions from 2 inputs to 1 output. I'm going to be training it to learn the OR function in a minute, right? So OR maps 2 binary variables, call them A and B, to 1 binary output, right? So if I want a weight matrix for 2 visible units and 1 hidden unit, that is a 1 row, 2 column matrix. And I'm initializing it with random numbers. This is not the smartest way to pick those random numbers. We'll talk about smarter ways to do that later. So I need a function for the derivative of tan h. TensorFlow will do this by hand. TensorFlow autodiffs. NumPy doesn't, so I just need to look up what the derivative of hyperbolic tangent is, and it's this. It is, so the derivative of tan h is 1.0 minus tan h squared. You just look that up, right? They just an identity that you can discover. So I'm defining my d underscore tan h, and I'm going to generate my data set, which I'm going to skip right now because that's just going to complicate looking at the pure forward pass, back pass. But I'll do an example in a minute where I'm going to use a specific data set. I'm going to define my learning rate. I'm going to use 0.01, which is probably much slower than I need to be for a problem this simple. And here's my kind of while not stopping condition. I'm just going to apply stochastic gradient descent 100,000 times. So 100,000 times, I'm going to pick something from my data set at random, pick an input and a label at random, and I'm going to use the random.choice to pick something out of the data set, which is a list. So data set's a list, random.choice grabs something from the list at random, and I'm going to use tuple unpacking with this comma to assign the first thing to x and the second thing to y. Then I'm just going to do y equals weight matrix w, matrix product x the input, to get y the preactivation, and then my output is just going to be tan h, which is my nonlinearity, times my preactivation. Okay? Pretty straightforward. Then my backward pass, and again, right, this is going to take care of computing that double sum, right, multiplying all the inputs by all the weights, and component-wise applying the activation function. And I am going to get a column vector, and I kind of did wiggle quotes because it's going to be a one-dimensional column vector, right? It's a 1-by-1 matrix that is my output. Then, in the backward pass, I'm gonna remember the calculus I just kind of powered summon before. Right? There's my error, we remember before. There's my derivative of the activation function, we remember from before. And there is the transpose of my input flipped, like my input flipped sideways, so it's a row matrix, and it's going to so it's a row vector, and it will blow this up into a matrix, right? And then I'm just applying that dw for delta w, right? I'm applying my updates multiplied by my learning rate and adding those to my weight matrix. So here is the first data set I'm going to use. Please still be good. So this is me training it for the OR function, right? These aren't really binary, right? They're floating point values. So floating point 0 for false, floating point 1 for true. These are my outputs that I want it to learn. Again, remember that I've kind of written this sort of double list style to make it a 2D thing. So it is a matrix, it is a 2D array. It's just a 2D array that is a 1-by-1, right? So it's a 2D array matrix, or it's a 2D array of size 1, or it is a 1-by-1 matrix that is the output I want, right? Why did I do 0.75? So that is because tan h asymptotically approaches 1 at infinity. If I used 1 here, I would be trying to train my network to output an actual value of 1. That means I would be trying to train it to produce a preactivation of infinity, right? Which is bad. I would be driving the weights to become huge, and that would make the network inherently unstable, right? Because, well, that might be tricky to get into right now because the gradient's going to vanish while it's trying to manage huge weights, and that's not going to work, right? So I'm going to use a smaller number of 0.75 so that it kind of, so that it stays in the curvier, not flat region of tan h, where the weights are going to have a more reasonable size. And if I train my network on this input, then I get this output. It didn't do perfectly, it did well. So basically, our network has inadequate capacity to make all three of these 0.75. With just 2 weights and 1 layer, it cannot make this sort of pre-input. That's going to have pre-input of twice either of these, right? With just 2 weights, it cannot map both of these to 0.75 while mapping the sum of them to 0.75, right? It has to be different, right? So again, our weight matrix is 1 by 2, right? So it needs to have a number that it can put here and here, right? We'll use W. All right. So it needs to have, so here's our weight matrix, right? It needs to have a weight, right, that for the 0, 1 case, it's this one, will be 0.75. And in the 0, 2 case, and in the 1, 0 case, this will be 0.75. But in the 1, 1 case, we'll sum both of these, right, and be 0.75. That can't happen, right? This is sort of the best that our network could ever mathematically do, is what I'm trying to say, because it doesn't have enough weights, it doesn't have enough learning capacity. If we graph the loss as time goes on, as time goes on, it looks like this, right? So even though we don't have the learning capacity to really learn our rule, we see that our random initialization starts out pretty bad, but that it extremely rapidly approaches the best it's going to do, right? Zoop. Learns very, very rapidly, and then stays more or less the same, slightly noisy. Because again, it's a little bit noisy because the same weight initialization, or the same weights that are going to work for the 0, 1 case are not going to work for the 1, 1 case. Now, if I train it on XOR, that's exclusive OR, right? Which is A or B, but not both. This is really kind of tricky, and we see that it just does incredibly poorly, right? So when it's trying to learn A or B, but not both, it just kind of fails. And if we graph the learning rate, it goes totally nuts. Or I'm sorry, if we graph the losses it trains, it goes totally nuts. And again, that is because there is no weight assignment out of a 1 by 2 weight matrix, right? There is no 1 by 2 weight matrix you could pick that is going to produce an output for 0, 1 that is less than the output for 1, 1, right? Well, okay, I guess technically you could. So that is going to produce an output for 0, 1 and for 1, 0 that is greater than the output for 1, 1, right? It can't happen. Butcher that a little bit, but. So what we're going to have to do is add a layer, but I think I'm going to stop right here for the time being because I've thrown a whole lot at you this week, all right? And if past experience is any kind of guide of future behavior, I imagine that some people are going to be completely overwhelmed, right? So I'd like to kind of go back very briefly and pick out the really important results. That's this, right? Remember, this is our forward pass in matrix vector notation, where this is a box of numbers and that's a column of numbers. And the output is a column of numbers. Well, okay. It would be nice to remember that the chain rule is how we kind of derive backprop, right? So the backpropagation isn't magical. We figure it out with the chain rule, but I'm not going to make you actually apply that. The result that you figure out ends up looking like this, or in Python, or Numpy Python, like this, right? Here's our magic update rule, where this and this are column vectors, This is a column vector. This is a column vector we flip sideways so it's a row vector. And this is a matrix. It's a 2D box. Well, and it'll matter for later. Remember that this is a term in here. Our weight update has in the middle of it the derivative of our activation function. That's important. And then here is our short description of a single layer network under gradient descent, right, minus where the data set comes from. Okay, so if we can look at this code and we kind of get an intuitive understanding of what it's doing, right? Here is the forward pass in matrix vector notation using Numpy. Here is the backwards pass, the weight updates, which we got from the chain rule, and we're writing in matrix vector notation using Numpy. And here we're actually applying that, right? And that this whole process of just picking and sample at random, computing like the error and the update for that sample, and then repeat, that's stochastic gradient descent, okay? If you're good on all of that, then I think we're good to go forward. And yeah, I think now I'm going to go write a homework for y'all, and please let me know in the in-class sessions how this goes. Well, how you understood this, right? Let me know if you kind of get this, if I blitz this way too quickly, if I blitzed it way too slowly, if it's not satisfying as a discussion, whatever, okay? Yeah, see y'all in the in-person session.